Hello, everyone. I'd like to welcome you to the Critical Materials Innovation Hub webinar series designed for CMI and by CMI. Today, we're going to have a presentation on the 2023 Critical Materials Assessment, and we're looking forward to that. I'd like to tell you a little bit about the webinar. These webinars are hosted by Colorado School of Mines, and today I am Cynthia Howell, and I'm going to be the moderator today. And if you have a suggestion for a future webinar, we always want to hear that. Please look at the CMI at mines.edu. I want to remind you this is a public webinar, and the recording is going to be available next week at aimslab.gov/CMI or on our YouTube or Critical Materials Innovation Hub channel. Questions, we are going to hold the questions to the end of the presentation, but that doesn't mean for you to hold writing them. Please make sure that you put your questions in the Q&A as soon as you have them, so we have questions queued up when our presenters are finished. I'd like to take some time to introduce our presenters today. We have Dr. Ruby Nguyen. She is the lead of the Systems Dynamics and Modeling Group in the Systems Science and Engineering Department at INL. Her research interests are to understand system impacts of energy sources, improve resource use and management toward a circular economy. Her PhD is in Environmental and Natural Resource Sciences from Washington State. And her co-presenter today is with Dr. Braeton Smith, an economist in Argonne's Decision-Making Infrastructure Sciences Division. His research focuses on critical material, supply chains, economic consequence analysis, and quantifying the economic benefits of infrastructure resilience. His PhD and master's is in mineral and energy economics from Colorado School of Mines. And Braeton, if you wouldn't mind taking it from here.
Thanks, Cynthia, and thanks everybody for joining today.
Welcome.
So today we're going to talk about the Department of Energy's 2023 Critical Materials Assessment. We're going to give you an overview of the methods that we used and some of the results and implications of the work that we did for the Department of Energy. So first, what is material criticality? So the idea of material criticality has been around for some time, but was really ironed out in a 2008 report by the National Research Council called Critical Minerals in the U.S. Economy, where they really identified material criticality as being materials that were both high in supply risk, as determined by a number of factors, and the impact of a supply restriction of those materials on some particular end use. So the perspective really matters here and can really influence what ends up being important to different stakeholders and from different what's important to one government may be different to another government, or what's important to a research organization may be very different than something that's important to a private company, or any variety of different perspectives you might have there. Why do we look at material criticality? Well, it's useful for informing strategy around certain supply chain issues. So if you know that something is a specific risk, you can either invest in different technologies or different things to avoid that. You can be aware of and manage those risks, or you can just basically just strategize around various supply chain issues if you know what your critical materials are. There are many existing critical material or material criticality assessments out there. These have been performed by governments around the world, different research organizations that may use it to prioritize where funding gets directed into different research programs or projects. And it's also used by private firms so that they may look at whether or not to pursue specific ideas based on the fact that certain materials may be difficult to get into their supply chains. So I want to be clear that this particular conversation we're going to have today is about the Department of Energy's 2023 Critical Materials Assessment. So even though this is a CMI webinar, this is not about an independent assessment that CMI conducts for its own R&D strategy. So the DOE has a long history of performing critical material assessments, which really began with their 2010 critical material strategy. This really laid out the framework for what ultimately became a pretty seminal paper in the material criticality literature, where they really were looking at what was really important to energy technologies that they really cared about. They repeated this analysis in 2011, went a little bit more in depth, and then also in 2019 in a report that recently became available. And then this is now the 2023 version of that. So the first one that has really been publicly available since 2011. Where does DOE differ from other assessments, such as the US Geological Survey or those done by like the European Commission? So we really have a focus on materials rather than specifically minerals. And we're really focused on the importance to energy and decarbonization rather than economic importance. So rather than looking at something that's important to the manufacturing base, we're really looking at things that are important for energy technologies specifically. The DOE assessment is also forward-looking as opposed to retrospective. And what that means is it's taking into account future demand and the penetration of future energy technologies rather than just looking at what's used in the economy currently. So you can see the two figures on the bottom there where we have, the traditional framework that we laid out, things that are both important in supply risk and important to clean energy would be critical. We have materials changing over time between the 2011 and the 2019 report. And then also materials were included in the 2019 report that were not included in the 2011 report due to different technologies being considered that weren't included previously. So the results from these assessments inform DOE research and development strategy over time. So the results from this specific assessment will be used over the next several years. And then in this case, these are also used to inform the critical materials list, which has determined the 48C tax credit that was part of the Inflation Reduction Act. So the 2023 assessment, we used three-step process to determine ultimately what materials were in scope, which materials would then become kind of the key materials that we would really focus on, and then which materials would become critical. So this three-step process, we had defining the scope, doing the screening on those materials, and then finally assessing. The scoping was really based on expert opinion and based on some supply chain deep dive reports that I'll talk about more on the next slide, determine the list of key materials so that we could avoid doing a long, exhaustive process of criticality, because it is quite an intensive process to do for each material, just to kind of downscale the list a little bit. And then finally, we have the criticality assessment itself, which is focused on those two factors that we talked about before, clean energy importance and supply risk. So talking about our in-scope materials, you can see on the left-hand column, we have the overall technology sectors that we are focused on, the relevant sub-technologies and components in the middle column, and then the relevant materials to each of those listed in the right. So it's a long list of materials, and you'll notice that it also includes not just minerals and elements, it also includes man-made or engineered materials like electrical steel and silicon carbide. So that's the first time we've really looked at that in one of the DOE assessments, is not just considering things that are what you might think of as just being natural raw materials. Where did we get this list from? This comes from discussions with subject matter experts within DOE, within industry. If you go back to the previous slide, maybe. Subject matter experts, as well as talking to or reading through the supply chain deep dive reports that DOE released on February 22 that were in response to President Biden's executive order on America's supply chains, where we really looked at all of the different materials and issues focused on supply chains for specific energy sector, industrial-based supply chains. So those are all available on DOE's website as well. Next slide. For the screening process, there were three metrics that we looked at. First being technology importance, second being importance of the sub-technology or specific component that we were interested in, and third was material importance. So for technology importance, you could think of this as the projected growth to 2030 in a net zero scenario from the International Energy Agency. So if we're talking about wind turbines, for example, you might think about this is the projected growth of of offshore wind in general relative to the energy mix. So a high score would have been something that's growing faster than GDP at a greater than 5% annual growth rate. For sub-technology, then, we would think about this as the importance of direct drive turbine or a generator that is using magnets or something like that. So very specific type of offshore wind turbine. And then lastly, for material importance, this would be the actual neodymium or dysprosium that's going into the magnet that gets used in the direct drive generator that gets used in the wind turbine. So next, so basically it is a weighted sum based on these factors. And if it achieves a maximum score that is greater than the threshold that we set, it would be screened in for inclusion in the criticality assessment. So the slide shows the results from that assessment. This figure is a little tricky to read, but basically these are the scores received by each material the screening methodology. So everything that is green would have been screened in because it received a max score above that threshold score of 22. And then everything to the right was screened out. So things like iron ore, for example, would have been screened out because the additional demand imposed by growth of these technologies would have been a blip on the radar for that market. And things like palladium and rhodium would be screened out because they are mainly used in catalytic converters, which are not expected to grow with the advent of electric vehicles. So things that are screened in tend to be things like graphite, nickel, cobalt, which are used in electric vehicle batteries, and the rare earth elements used in magnets and several other materials used in semiconductors. So given that a material is screened in for inclusion in the criticality assessment, we would then apply the criticality methodology to it. So this methodology is similar to what has been performed in previous Department of Energy critical material strategies in the past, with a little more definition around some of the factors that we have here. So as I mentioned, criticality is defined by these two primary factors, clean energy importance and supply risk, each of which is a weighted score based on these different factors listed here. And each of the factors here was range between 1 and 4, with 4 being it is either more important to clean energy or contributes more to supply risk. So the first one, clean energy importance, we have energy demand and substitution limitations. Energy demand is really focused on the expected growth of energy technologies and the amount of material that they will use for those. That receives most of the weight for clean energy importance. Second is substitution limitations, which is really the idea that something might be more difficult to replace in an existing technology. And this could be both at the elemental level as well as at the technology level. Next, we have supply risk, which is a score based on these 5 metrics shown below, starting with basic availability, which receives most of the weight. Basic availability is basically the idea that it's the production and the expected production of a material versus its projected demand. So projected demand in 2025 or 2035 relative to the current production of that material. Competing technology demand is the idea that there are other technologies out there that may be users of the material that may crowd out the ability of energy sector users to get that material. Next is political, regulatory, and social factors, which is also a weighting of where a material comes from and to what extent those locations are either geopolitically sensitive or struggle with environmental, social, or some other factors. And these are really based on the World Bank's world governance indicators, as well as some measures of environmental performance based on the country level. Next, we have codependence on other markets. This is the idea that certain materials, specifically minor metals, are often not the higher value product at some mines, and so they may not actually be the determinant of what gets produced. So for example, material like iridium is a platinum group metal, one of the rarest metals on Earth, but is always co-mined with platinum and palladium, which platinum and palladium will always guide basically the decision of whether or not whether or not to mine iridium. And so it would receive a 4 in that category. So that's a huge supply risk for certain materials that do not drive investment decisions on their own. And lastly, we have producer diversity, which is a measure of market power. And this is the idea that a material may be completely controlled by one specific entity that would have the ability to exert some control over the market if they decided either to lower prices or flood the market with new supply or restrict supply. With that, I'll turn it over to Ruby to discuss some of the findings and application of these methods.
Yeah, thanks, Braeton. And also on this slide, we just want to tell the timeline of the report. So the short term is between now and 2025, and then the medium term is until 2035. So here we just want to clarify some of the points to support the supply risk assessment. So as Braeton mentioned, there are quantitative and qualitative information. In terms of basic availability and competing demand, we base on International Energy Agency (IEA) scenarios. Sometimes we have to rely on trade associations projections as well as market reports for the technologies that IEA doesn't have projections on. So the 4 main trajectories that we were considering include 2 dimensions. One is the market penetration of that specific technology and the material intensity used for that technology. So for market penetration, low penetration meaning stated policy scenarios, and then high trajectories meaning high or aggressive decarbonization goals. For material intensity, the high intensity resembles current technology, whereas low intensity assumes that's what the future technology will achieve. And so of these 4 combinations, trajectory B is closer to business as usual, whereas trajectory C is the most optimistic scenario where we have high deployment goals and then low material intensity. So on this chart, you can see the 4 scenarios. That's the total material demand for one material. And then we also include non-energy demand in the black line here. We also look at production and production capacity to see what's the gap between what we're producing or what our capacity right now with the projected scenarios. So along the lines of the wind example, we want to give an example of how we assess neodymium. So for importance to energy, for both the short and medium term, neodymium used in wind energy technologies has pretty high market share. So we gave this material a score of 3 for both short and medium term. This material is substitutable. However, you will encounter major limitations with substitution. So we also gave a score of 3. So aggregating the weight, we have a score of 3 for importance to energy, both in the short and medium term. Now moving on to supply risk, the basic availability, as you can see here, most of in the short term, 3 out of 4 scenarios go beyond the current production capacity or production level. And so we put the basic availability at 3. But in the medium term, then you can see the gap is getting even more significant. That's why we give it a score of 4. For competing technologies, besides wind and EV traction motors, there are some other technologies such as electronics and household appliances that also use neodymium magnets. For political and social factors, as is highly related to the producer diversity. So neodymium is a rare earth production is highly concentrated in China, as we already know. So that it has a high risk score here, which impact the political and social factor score. And then in terms of market codependence, neodymium is not major products like copper, or aluminum, or iron. However, within the rare earth suite, then neodymium is still the economic decision driver for rare earth production. And so aggregating all these scores, then we have three supply risks in the short term and medium term, four. So moving on to the results of this assessment. So we screened in 23 materials. And for those who read this for the first time, it might be a little hard for you. So I'm going to walk you through. So if you look at the top right corner, that's the critical material zone. That means those materials have high importance to clean energy and also high supply risk. So we have 7 materials here. So dysprosium, neodymium, terbium are magnetic materials used in wind turbines and EV traction motors. Gallium is used in electronics, and in this case, mostly the LED lighting technology that we care about. Cobalt and graphite are battery materials used in EVs and energy storage, and iridium is used for hydrogen technology. Now, in the yellow zone is called the near critical zone, meaning these materials have high score in one dimension and average score in the other dimension. And then finally, we have the green zone, which is the not critical zone. Now, so that's the short term, and then we move on to the medium term. And as you can see, the critical zone becomes more crowded. So there are 6 more materials that joining this group moved from the near critical zone in the short term. So lithium and nickel are joining the battery materials. Platinum's joining iridium in the hydrogen technology. Magnesium is for lightweighting. Silicon carbide is also used in power electronics. And then you can also see, aluminum move from not critical to near critical, same as copper. So we just want to compare with the 2019 results to understand the dynamic of the criticality. So for the short term, as you can see with the 2019, there are fewer materials to look at. Dysprosium, gallium, and neodymium are critical, just like our current one. And rhodium was screened out due to technology change. With the medium-term assessment, we have lithium, cobalt, magnesium here. So very similar results, except for rhodium, and there are more materials that we considered. So a quick summary of the results. There are materials that used to be critical then, but not now anymore, like rhodium or palladium, because of the change in the declining of the technology of catalytic converters. There are materials that are critical now, but not then. So a lot of these are like hydrogen materials, as I mentioned, or batteries and energy storage, as well as some of the engineered materials, as Braeton mentioned in the beginning, like electrical steel and silicon carbide. So the implications of our analysis is that it helps support DOE decision in determining the list of critical materials. This list also helps guide DOE strategize their research, development, and deployment on critical materials, as well as other energy supply chains. This list, in combination with the USGS 50 critical minerals, are used to determine eligibility for tax credits under the Inflation Reduction Act 48C for projects involved in processing, refining, or recycling of these critical materials. So this program is overseen by the Office of Manufacturing and Energy Supply Chains, or MESC for short. So the MESC office partners with Department of Treasury and the IRS. The tax credit could be up to 30% of the qualified investment for the projects. The MESC has set aside $10 billion through the Qualifying Advanced Energy Project Credit Program and $4 billion for projects expanding clean energy manufacturing, as well as recycling and refining of critical materials. So in conclusion, we've discussed this assessment. We evaluated more than 40 materials used across major energy technologies, and 23 materials were screened in for the criticality assessment. So between now and 2025, there are 7 critical materials, and then there are 6 more by 2035. And because criticality changes over time, depending on the technology condition, mar- market conditions, social and environmental conditions. So the criticality will also change over time, and DOE plans on update this assessment periodically. And with that, we'd like to thank your participation and happy to answer any questions you might have.
Ruby and Braeton, I want to thank you so much for such a great presentation on behalf of the group here viewing. It was really interesting to hear of the research assessment process that you have engaged in to help come up with the critical materials, and also to discuss the importance of the assessment findings and what that means in the future. And again, as usual, there will be more updates as DOE and others look at this information into the future. As you mentioned in your last comment, there are a lot of things that happen that can change criticality of these materials. So thank you for this great presentation. And right now we're going to start our Q&A session. I have 2 questions queued up. The first one is from John Omarad. Why is praseodymium not included in the 2023 assessment, since most of the neodymium ferrous boride magnets use neodymium praseodymium binary alloy?
Sure. So we did look at praseodymium. It did have a different criticality than neodymium in the short term, but in the medium term, it also becomes critical along with neodymium. But a good question for the future as we're looking at certain manufactured materials or engineered materials as well, maybe looking at a didymium or the NdPr alloy on its own, maybe independent of neodymium and praseodymium, would also be worthwhile for future assessments.
So we have a next question from Ariel Fahimi. How do social issues are influencing criticality, or how are social issues influencing criticality?
Yes, I'm going to take this. So the way we evaluated the political, social, environment factors is to use the world governance indicators. So these world governance indicators are developed by the World Bank, and so they evaluate, in different dimensions. But in general, like not only the political conditions, but the social conditions can also impact the workforce and the manufacturing of certain country, and that's how it can impact the supply of critical materials globally. So that's the connection between the social factors and criticality.
Okay, we've got the next question is from Dan Gainesar. Nice presentation. And why is, and I'm going to let you guys tell me what these are, SI and T not considered to have high importance to clean energy when both are needed for high efficiency solar cells?
So Dan, the silicon is included. Let me see if I can.
So I can comment on these. So silicon and tellurium. So really, so you've gotten this question a lot from users who have a specific end use in mind. And while silicon and tellurium are important for solar cells, they may not be as important in the broader energy system. So things that are really important tend to be used in multiple technologies or used in technologies that are going to contribute more to the energy system. Their use will be greater, larger share of production, or demand is expected to be greater for them in the future. So not importance to a specific end use. This kind of gets to the perspective question I was talking about at the beginning, but important to the energy system overall.
So I would add to that, Braeton, that we did consider CATL solar technologies. And with this assessment, it's a global projection. So globally, CATL adoption is still very low, between 3 and 5% compared to silicon panels. And so only in the US that the adoption rate is like 40 to 50%. And the USGS assessment already included tellurium as important to the US economies. So we just want to offer a different perspective on the clean energy technologies. But I would say at the end of the day, because the two lists inform the tax credit and the criticality moving forward, I think we kind of capture both importance.
We have a next question from David Reed. Perhaps you said/showed, and I missed it, but how does the domestic availability enter into your assessment?
So I actually neglected to mention this at the beginning when we were talking about what differentiates this assessment from others. This was really focused on the global perspective. So global ability to meet potential climate goals. So this was not a domestic focus. We didn't really look at domestic availability. We were looking at availability across the board.
So our next question from Ario again. We just said a thank you. We'll move on to Fernando Alaron. Great presentation. Copper is not considered critical, ?
Yeah, so I have to show the results again. So yeah, for our results, copper is near critical. So it's not, it has not rise to the level of importance compared to other. But copper is included in the DOE's critical material list. Yeah, so for that list, DOE consider all the materials that are critical and near critical in both the short and medium term.
An important point there that I want to iterate too is that the critical materials assessment is separate than the critical materials list. So the critical materials assessment informed the determination by DOE on what should be included on the critical materials list. So yes, copper is on the critical materials list, but in this assessment, it's near critical in the medium term.
I want to urge anybody in the audience again, if there are any more questions out there. I'm not seeing any others. And Braeton and Ruby also, is there anything else that you would like to add in conclusion of your presentation? Gives
No,
people a
I
little bit
just
of
like
time.
to thank for the opportunity to present and a high number of participants. So very excited about this.
Yes, likewise. And also our sponsor for this work was the Advanced Materials and Manufacturing Technologies Office, which are called AMTO, which is also the funder of CMI. So thank them for their help and guidance in all of this work as well.
We also have one quick question, Jaylee. Can you share your slides?
Yes, but not immediately.
So those will be made available in the future.
Yeah, and we just want to let you know that the full report is available publicly, so you can access that report. And it has all the information that we presented. We just condense it in a more digestible form. We also want to acknowledge that even though it's just Braeton and me presenting today, but we had a team of 20 people working diligently for a year on this. So this is a gigantic task, and it was an honor to do this work on behalf of the AMTO office.
Certainly.
Sounds good, and I'm not seeing any additional questions here. So what I'd like to do is, and keep the question in your eyes here, just in case I miss it, but I want to thank you all for attending. The recording is going to be available next week at aimslab.gov/CMI, and again on the YouTube channel. Watch for details about the next webinar in Critical Times newsletter and on social media, which are your regular places. We have a lot of new members here, and again, want to make you aware of the fact that this is pretty much a monthly event, and you'll see some new topics coming out in the new year. Please let us know what your suggestion for a future webinar is. We like to honor that as much as possible because these is a webinar series that is designed for you. So thank you again for your attendance. Thank you again for Ruby and Braeton for a great presentation and a very interesting topic for all of us as we go forward working in the critical materials field. Thank you again.